Sneezes only. All right. So at this point, I think everybody's probably had a chance to do the Delta Math registration. Once you've done that, go ahead and fire up Microsoft Teams. This will be the only time we use Teams for the entire semester is just today to do this. I noticed on my computer I have like work and school teams and non-work and school teams. Make sure you use the work and school teams because I don't think it works otherwise. I was like, why am I getting this log on stuff? Shouldn't this just open? And I went, oh, that's why. I have the wrong teams. I don't know why I have another Teams on here. When you log into Microsoft Teams, you should see a tile for 7th hour pre-calc. Go ahead and click that. Actually, before that, does anybody not see the 7th hour pre-calc tile? Boy, oh boy, I did a bad job here. All right, let's see here. All right. Nolan, you said you don't. Tompkins, okay, and then Kendall. Okay, who else? Ava. What in the world did I do here? This is my worst class. And then CJ, probably go with the last name there. Ugh. There we go. That's it. And then Ariana. Okay. And then John Paul. Drew, you too?
Yeah, I just loaded this up.
That's okay. When I type your name in, do I do Drew or do I have to do?
Try John first.
Okay.
No.
Not John Smith, teacher.
No. Okay, try Drew.
Drew Smith.
Yeah.
And then John Smith is the username. That's super confusing. All right. Everybody else okay? All right. I'm going to go ahead and hit add on that. If you guys refresh here in a minute or whatever, you should see that stuff go through. The catch is the next part is slow if you're just getting registered. If I'm just adding you now, because it has to do like communicate up and down to the cloud a bunch of times, so it takes a minute. All right. Once you got your 7th hour tile, which again I think if you guys refreshed you'd see it now. Go ahead and from the navigation pane here on the left, click Class Notebook. On the right, you'll see a OneNote frame kind of pop in there. From there, where it says Open in Browser, click the drop down and pick Open in Desktop App, and then you're done. Now, those of you that I just added, it's going to take a long time possibly for the OneNote to populate in there. Just like leave it running in the background or whatever and check it again in a few minutes. No big deal, right? Okay. Worst case scenario, you try tomorrow and it should be due real fast, but it takes a minute to populate or whatever. I try to do it in advance and not make a mistake, but boy, oh boy, I don't know what I did to this class because it was all mistakes. So I don't know. I have no excuses. All right. Any questions about getting the OneNote set? Okay. So if you haven't had my class before, most of what I do is going to be done inside of OneNote. So when you open up your OneNote, you're going to see 3 tabs at the top. Your collaboration space, I don't use that for anything. Content library, that's where I put anything that I'm going to share with you, just kind of goes into the content library. And then the third one will be your name. inside your name, you'll see a section for notes and a section for the homework. I check all of the homeworks through OneNote. When it gets closer to the OneNote or to a homework due date, we'll kind of talk about how that works. If you had me last semester, it's going to work the same way. If you're new to this class and you're not familiar with OneNote or you need some help, ask anybody that had me last semester, and they should be close enough to an expert to be able to help you kind of figure out what's going on. Or you can talk to me. That's fine too. So here inside of the content library is the syllabus. I also have it up on the My Notre Dame page that you could download. This is the exact same syllabus from first semester. The only difference is the stuff that's being covered. If you're new to me this semester, probably take a minute and read through the syllabus. But it's, like pretty standard stuffs. And then if you are new to me this semester, I'd also appreciate if you filled out like the syllabus sheet. So if you had me first semester, don't worry about this. But if you are new to me, I would like you to do this. Anytime next week is fine. You can do it, give me a physical copy, or you can do it digitally in OneNote. Just drop it into your OneNote, and that's fine too. Either way is not a big deal. And if you forget by the end of next week, I'll probably send you an email reminder or whatever. But make a note to yourself. And again, there you can get this from the OneNote, or if we look at the My Notre Dame syllabus sign-in sheet as a separate. If you just want the sheet to print or whatever, that's fine too. Okie dokes. Okay. So topics covered in second semester. So we can start with chapter 7. I know some of you guys coming from Miss Morgan's, you didn't quite finish chapter 6. It's not a big deal. There's not a lot of overlap from chapter 6 on, so we're just going to start at 7. Everyone will start in the same place. If there's anything that comes up where it's like, oh, this was a chapter 6 thing, we'll redo that part when we need it. But we're just all going to start at 7, I think, rather than redo, stuff for, 5 of the 20 people. You know what I mean? It's just like, what do I do with this? I'm not going to ask you to do anything extra. It just is what it is. So I think in general, second semester for this course is easier than first semester overall. I do think the single most difficult topic for the course happens in second semester, and it's probably this chapter 8 is probably the single most difficult topic. But I think the rest of the stuff is very similar or really straightforward, or just redoing of things that we've done in Algebra 2. So in general, I think this tends to be the easier of the 2 semesters. Maybe not by a bunch, but by a little bit. All right. So let's start here today with chapter 7. And we'll just kind of get this show on the road. All right. So kind of our motivating question here, motivating idea, is going back to either first semester of this course or possibly even back to your geometry course. We're often interested in this kind of problem. We're asking you to solve the triangle. Now, in the event that it was a right triangle, this was pretty easy. We could just use SOHCAHTOA and or the Pythagorean theorem. And that's really all we needed to be able to find side lengths and angle measures inside of a right triangle, right? We did that a little bit first semester. You probably did it a lot in geometry. So the question then should become, what if I have a non-right triangle? Can I use SOHCAHTOA? No. Can I use the Pythagorean theorem? No. Okay, so we'll have to construct a new method to deal with that kind of situation. So let's just say we have some generic non-right triangle. This triangle ABC will be my example here. Remind you guys the naming convention we use when labeling a triangle is that if I've named this as vertex A, the side opposite vertex A needs to be named with a little a. You guys all remember kind of doing that? Need to make sure that we're naming things using that convention, or the formulas will not work that we're going to build out. So all these formulas that we're going to build rely on using this naming convention. All right, so here's my generic non-right triangle. Oh no, what do I do? All I know about is SOHCAHTOA and the Pythagorean theorem. Well, I'm just going to drop an altitude from one of the vertices. The altitude I'll drop from is C. And let's say that the length of that side is h then. Why would I want to drop an altitude? Well, it's because it makes me two right triangles, right? I have a right triangle here in yellow and a right triangle here in blue. And as long as I'm just working inside of those right triangles, I can use SOHCAHTOA or I can use the Pythagorean theorem. So for example, if I look in the yellow triangle, I can say that sine A is equal to opposite over hypotenuse. If I look in the blue triangle, similarly, I can say that sine B is equal to opposite over hypotenuse. When I go and I look at these two equations, what do I notice? Both of these equations that I've written involve h, which I don't know anything about. I just know it exists. But what I can do is I can treat this like a system of two equations, solve each of these two equations for h, and then like stick them equal to each other. So the equation here on the left, I'll multiply both sides by b to get the h by itself. And the one on the right, I'll multiply both sides by a to get the h by itself. And since both of these equations are equal to h, I can set them equal to each other. And what I have now is an equation that'll work inside a non-right triangle that involves nothing but the angle measures and side lengths of that right triangle or that non-right triangle. Everybody's cool? Now, this is not the typical form that we represent this equation in. So what I'm going to do is I'm just going to divide both sides by AB. So the B's cancel on the left and the A's cancel on the right. And we're left with sine A over A equals sine B over B. And I can extend what I'm doing now. So if I go back to my original, I can draw another altitude. Say I draw that altitude and repeat the process. I'd get here that sine B over B is equal to sine C over C. And if I did it again, I would get that sine C over C is equal to sine A over A. Basically completing that, my formula here that we'll call the law of sines. I abbreviate that as LOS for law of sines. And this is a formula that I can use inside of non-right triangles. Will it also work in right triangles? Yeah, it'll work there too. Is it kind of harder than it needs to be to use in the right triangle? Yeah, I mean, I'd rather just do SOHCAHTOA or Pythagorean theorem or something, but this still works, which is what we want in mathematics, right? If we take something general, or we generalize something, we want it to still work on the thing that we had before. We just want it to work on other stuff also. All right, so let's look at a couple of examples here using the law of sines to solve a non-right triangle. So in triangle where angle A is 32 degrees, angle B is 73 degrees, and side C is 13 inches, we're asked to solve this triangle. So that's going to mean we have to find angle C, side A, and side B. Everybody agree with that? First thing I would do is draw myself a picture of what's going on. Now, I don't really care about the scale of the picture. Every time I draw my triangle, I draw the exact same looking triangle. Even if it looks like an acute angle and I label it as 115 degrees or something, like, I just really don't care. Personally, it's just something for me to visualize to make sure I get the things in the right place on my formula. So the big key here is to make sure I label my side lengths correctly. So again, angle and opposite side need to be labeled with the same letter. And then I'll draw in my givens. So to use the law of sines, I need to have one piece where I know both the side and the angle. Well, I don't know that for A. I don't know that for B's. And I don't know that for C's. Doesn't look like I can really use the law of sines in this problem. I can find C right away, right? So that's absolutely right. So that's the first thing I would need to do, is I need to find angle C. And I can do that because I know there's 180 degrees in a triangle. I can find the value for C by just subtracting 32 and 73 from 180. Was that minus 105? So that should be 75 degrees then. So now I have an angle and a side that I know. All right, so now I'm ready to use the law of sines. Does it matter whether I solve for side A or side B next? Nah, man. At least not for this kind of problem. In the future, as we get a little bit further in, it can make a difference what order you're doing things in. But for these problems, it does not. So I'm just going to use, what should we do? Let's find side A first, for no better reason other than the alphabet, that A is the first letter. Sound good to you guys? So again, since the law of sines, each of these three fractions are equal to each other, I can take any fraction, set it equal to any other fraction, right? They don't have to be physically written next to each other in the formula. Here I wrote sine C over C equals sine A over A, right? No big deal. Can use it all willy-nilly. So this kind of equation we have where we have one fraction equal to another fraction is called a proportion. Remember that from geometry. How do we solve a proportion? Cross multiply and divide. Exactly right. So we'll multiply here to get a times sine 75 equals, and then multiply there, 13 times sine 32. To get the a by itself, we'll divide both sides by sine 75. And now it's calculator time. Before I go start bombing away plugging this stuff into my calculator, what should I check? Yeah, I need to make sure I'm in the correct mode. We should be in degree mode here. How did we know that we needed to be in degree mode? The angles are in degrees. Yeah, very good. So I'm checking my calculator. I am in degree mode because this is like the 4th time I've done this since the school year started. So I'm good. You guys, it's probably been 3 weeks since you've opened your calculator. Probably be a good idea to check before you start grinding away at problems, getting, crazy answers because you're in radian mode or something. All right, so get out of there. To type this into my calculator, I'm going to use the fraction bar so I can type it in exactly like it looks on my sheet of paper. To get to that option, I press alpha, y equals, and then choose option 1. I like this because I like doing it this way because it really helps me avoid making any silly like order of operations or parenthesis mistakes like I would if I just typed it into a single line on my paper or into my calculator. So I can just type it in exactly the same way it looks on my sheet of paper. So I get about 713, and I think the unit on this problem said it was in inches, or the other side length was in inches, so this one should be in inches. Guess we could box that one up too. Okay, so now I know 2 of the 3 sides. To find the 3rd one, I can just use the Pythagorean theorem, right? No, why not? Not a right triangle. What should I do? Yeah, we just do the law of sines again. So here, does it matter whether if I use sine C over C or sine A over A, since I know both the angle and side for each of them? No, it doesn't matter. Which one is Mr. Kulik going to choose to use? C over C. Why? It's given, which means that I didn't have to do any rounding involved. So I know that this will give me the slightly more accurate answer. Now, as far as we're concerned, it really wouldn't make much of a difference if we're just going to round to 2 decimal places anyways. But if you're like landing a rocket on the moon for NASA or something, take the more accurate way of doing it. Like 0.1% off and your rocket misses the moon. Like, whoops, there's $1 billion down the drain. But obviously we're not trying to land rockets on the moon here, so it's not that important. So again, to solve for B, I'm going to cross multiply and divide. Is everybody okay with me just like shortcutting the cross multiply and divide work to just write down what I'm typing into my calculator? You did a bunch of it in geometry. It's not too bad, assuming that Mr. Kulik doesn't just make like a bonehead mistake and misread his problem or something. So I get 1287 for my other. Everybody happy? one quick thing we can do is a kind of a pseudo check. If I go back and I look up here, the pseudo check that I can do is I remember from geometry that the biggest side should be opposite the biggest angle. I see that 75 and 13. The middle side should be opposite the middle angle. That's what I'm seeing with 1287 opposite the 73. And the smallest side should be opposite the smallest angle. That's what I'm seeing there. Is this a 100% check? No. But if you make like you royally screw something up, this will catch it. Everybody cool? So far, so good? Pretty easy? Not too bad, right? All right, let's do another example here. So another example here, we have angle P is 43, angle Q is 80, and side Q is 7.3. So again, I'm just going to start by drawing my picture. What do you think I'm going to pick for my third vertex letter? R. Not because I love pirates, but the alphabet. I mean, if you love pirates, that's fine too, but I like the alphabet. So again, when you're labeling your sides, again, be careful. Make sure you're using the convention that the side is labeled with the same letter as the angle that it's opposite. So here we're looking for angle R, side P, and then side R. Now, straight away, I could solve for what two things first? I have two choices. Angle R would be one of them, and the other is side P. Excellent. Yes. Either one of those you could do first. Does it matter which one you do first? No, man. Which one do you think I'm going to do first? Angle R. Why? Because it's really easy. So what is that? 57? Everybody's good with that? Okay. Now again, now that I know angle R, I have enough now to solve for either little side R or side P. Does it matter which one I solve for next? No. Which one am I going to use? I'm going to do P because, well, the alphabet. So I'll write sine Q over Q equals sine P over P. I'll cross multiply and divide. And then it's just calculator time. Put 2 decimal points there? I think I did. So I have, what, 506 thereabouts? I think these were in centimeters. And then lastly, I'll find side R. So I'll do the law of sines one more time. And again, I could use sine P over P here instead if I wanted to, but I would never do that because I would rather use the non-rounded values if I can. Some problems you'll not have a choice and you'll have to use a rounded number, and that's okay, right? There's nothing wrong with using the rounded number, but I just prefer not to if I don't have to. So what do I got here? 622. Okay. Put on your membrane caps. Recall from geometry our triangle congruence theorems. Typically, we name these with like a 3-letter acronym. There's 5 of them. Does anybody remember any of them? Angle, side, angle. Angle, angle, angle is a similarity one. Side, 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 and side, angle, side, I heard people say, are both congruence ones. Hypotenuse leg is one of them. I'm going to put that as 5. There's one more. It's angle, side, angle is the other one. So hypotenuse leg is the special case of SSA. What's special about the hypotenuse leg situation is that the A has to be a right angle. So these were congruence theorems, right? Oh, I meant angle, angle, side. Sorry. Thank you, Ava. So, oh boy, what just happened there? Okay. So this is I don't know, I don't care anymore. Make a spot. Those are law of sine situations. These two are law of cosine situations. This is also a law of sine situation. But really, it's the SSA that's the law of sine situation. And since we don't have guaranteed triangle congruence, we call this guy, or this situation, the ambiguous case, because we could have 0 triangles possible, 1 triangle possible, or 2 triangles possible, depending on what the values are for my side, side, and angle. So it becomes pretty clear that I'm going to have to recognize what situation it is from the picture so I know whether I should be using law of sines or cosines. And even if I'm using law of sines, do I have to be like really careful about what I'm doing to figure out, like, is this problem even possible, or are there 2 sets of answers or just 1 set of answers? So let's go back and look at the pictures we've just drawn and decide which situation we were running into. Okay? Well, this is a lot of stuff going on here. All right. So let's take a look at this one. The stuff in red was our givens. So ignore the stuff in blue that we wrote in afterwards. What situation is this? We have 2 angles and a side. So is it angle, side, angle, or is it angle, angle, side? This is angle, side, angle. Very good, Kendall. So what you're looking for is, if I look at angle A and I look at angle B, C is an arm of both of those angles, right? The other side we're given is a part of both of those angles. That's what angle, side, angle looks like. Everybody's okay there? Let's go back let's go and look at the other one we did now. If we do the same thing here, I notice that side Q is not a part of angle Q. You guys see that? So in this case, this is angle, angle, side. That's the difference between those two, just by looking at them. Everybody's okay with that? Okay. So if you have an angle, side, angle, or angle, angle, side, those are the easiest two situations to deal with. They're just law of science problems. Nothing funny can happen. They're all possible. Nothing weird goes on. You don't have to be careful about what you're doing. You can just attack it right away and just get her done. Everybody's okay? The law of science situation we have to be careful about is this SSA situation. So let's talk a bit about how that situation is going to work. So recall that SSA on its own is not enough to guarantee triangle congruence. So just to kind of illustrate that, let's take a look at this picture. So triangle like ACD is clearly not congruent to triangle BCD. Everybody agree with that? Two totally different looking triangles. However, they do have SSA congruence, right? That A is congruent to B, side AC is congruent to side CB, and side CD is congruent to side CD. That this is SSA congruence. But we have two distinct different triangles. Everybody's cool with that? This is why this situation we have to be super careful about, because we're not guaranteed of even triangle existence or not. Okay? All right. So let's say that we're given angle A, we're given side A, and we're given side B. Those are the givens in our problem. Everybody's okay with that? So the first thing we're going to do is we're going to look at the size of angle A. If angle A is greater than or equal to 90 degrees, what kind of triangles do we have? Or what kind of triangle do we have, I should say? Obtuse, or, if it's equal, a right triangle. Everybody agree with that? Okay. How many obtuse angles can a triangle have? One. So that's guaranteed to be the biggest angle in the triangle, correct? How many right angles can a triangle have? 1. So that's guaranteed to be the biggest angle in the triangle, correct? So, if in that case, then we have that the side opposite AB is less, or the side opposite angle A is less than or equal to the other given side. What does that mean? So we have not the longest side opposite the biggest angle. Is that possible? No, right? So those are impossible situations. So I have either of those cases, can't have a triangle, because basically the hypotenuse isn't the longest side. Everybody's okay with that idea? Now, if the hypotenuse is the longest side, there's no problem. There's just one set of answers. That's a problem we can do. Everybody's okay there? All right, what if angle A is less than 90 degrees? What kind of triangle do we have there? An acute. How many acute angles can a triangle have? Well, it could have one, it could have 2 or 3, right? Okay. Do I know that angle A is the biggest angle? Do I know it's the smallest angle? Do I know anything about the size of angle A relative to the other angles in my triangle? No. So this is the hard one. Okay. So in this situation, if the side opposite that acute angle is bigger than the other side or equal to it, that's our friend. We just get one triangle. If the side opposite angle A is the smaller of the two sides, this is specifically what we refer to as the ambiguous case. Because just from looking at the measurements, we can't tell whether there's 0 triangles, 1 triangle, or 2 triangles. So if we have an SSA with an acute angle, and the side opposite the acute angle is the smaller of the two sides, more work is required to figure out what's going on. But that's the only situation that requires further analysis. Everything else I can tell just by looking at the givens. Everybody okay? Let's do an example. Let's say we want to solve the triangle where angle B is 48, side B is 10, and side A is 12. So first thing I'll do is I'll just draw my picture out. Now that I've done this, I should check to see if this is SSA or side angle side, right? Everybody agree? The way we check that is we look at the angle. Are the two givens, or the two sides that are given, make up the arms of the angle? No. That's the side angle side situation if it was. Here we have side side angle, since the two givens are not the arms of our angle. Everybody's okay with that? Okay. So it is SSA. So now we need to check that given angle. Well, that angle's acute. Okay. Then we need to check compare the side opposite my given angle to the other side that's given. And that is the smaller, so we are in the ambiguous case situation. So we have to determine whether we have 0, 1, or 2 triangles. Everybody okay with how I determined that what was going on? Okay. Let's show you how to make that determination now. What we're going to do is we're just going to set up a law of sines. So those are the two parts that I'm going to use. I'm going to say sine B over B is equal to sine A over A. And now I'm going to solve for sine A. So I'll just cross multiply and divide. So let's think back to first semester now. What's the biggest value that sine can have? So think about the unit circle. The sine is which coordinate on the unit circle? Y. What's the biggest y coordinate on the unit circle? 1. So if that value there is greater than 1, what does that tell us? No triangles are possible. It's an impossible situation. Okay. What angle does is sine equal to 1? 90, which means that we'd be in the hypotenuse leg situation, where that angle is 90 degrees. That means we have only one triangle possible. So if that number then is less than 1, that must be the 2 triangle situation. Is everybody happy with how to make the determination? Okay. Let's go ahead and type this into our calculator and see which one we run into. .892. So we have 2 triangle situation. Everybody cool so far? This tends to be the most difficult thing in chapter 7, is just doing these ambiguous case problems. So not bad that we're hitting the hardest thing in this chapter on day 1. I'll take it. And this isn't too bad, right? You just have to get comfortable figuring out what's going on. In my experience, in these ambiguous case problems, one of the things that gives students problems is just organization. So they get turned around in terms of like which information goes where. So when I do these kinds of problems, I like to be really clear and organize my work so the stuff for triangle 1 is all in one place and the stuff for triangle 2 is all in one place. So to solve this triangle, we need to find angle C, angle A angle C, and then side C. And because I have a set of values for each triangle, I'm going to add a subscript to my A's and C's so that it's clear to me like which triangle does this number belong to. Just really trying to make sure I'm keeping everything where it needs to be. Everybody so far so good? Okay. So for triangle 1, I'm going to start with this piece of information, that sine A is equal to 0.892. How do I solve that equation for A? If I have sine A equals 0.892, how do I solve that for A? I guess I should call that A1 now, huh? Very good. We'll do the inverse sine of both sides, which basically says that A is going to be the inverse sine of 0.892. So I'll go to my calculator, second, and then sine, and then I'll use the ANS command to grab that previous answer and all of its decimal points. So that gives me 63.10, I guess. Does everybody feel good? No big deal, right? Exactly the same as what we've been doing. If I want then angle C1, that's really easy because now I know 2 of the 3 angles. And it's unavoidable that I'm using a rounded answer here, and I'm fine with that, since it's unavoidable. So there I get 68.90. So far, so good. Then to find side C, I'm just going to use the law of sines again. So now that I know angle C, I can just set up another law of sines and just cross multiply and divide, just like we did in the previous examples. I know, me too, guy. So 1255 there. And what unit, did we have a unit on this? I don't think we did we? Okay, so triangle 1, basically the same process that we've been doing, right? Nothing tricky here. Triangle 2, the only tricky part is how to start this. So the first angle we solved for was A. So the first angle we're going to solve for in triangle 2 is going to be A. And here's the trick. Angle A in triangle 2 is going to be the supplement of angle 1, or of angle A in triangle 1. So I'll just do 180 minus that answer. So 116.90 or thereabouts. Everybody's good there? That was nice, right? That's even easier than it was on triangle 1 because I didn't have to use the law of sines. Just had to remember that it was a supplement of the other answer. Now to get angle C, well, that's easy now. I know angle B and I know angle A. So I can just use the triangle sum theorem. Common mistake I'll see students make is they'll use the supplement for both angles, not what you want to do. Only the supplement for the first angle you found, and then you're using the triangle sum theorem after that. So I get 15.10. And then I'll do the law of sines, just like I did in the previous problem. So sine B over B equals sine C over C. So when I solve for C2, do that, and just calculator time. What do you guys think on this? So 350 is what we got there. That's not too bad, right? Lengthy, right? There's 6 things you got to solve for, but none of them are terribly time consuming to get. And the process is basically identical for every SSA problem that has 2 solutions, or 2 sets of solutions anyways. So I think it's pretty okay. Pretty okay. For you guys, homework I'd like you to work on for next time would be 1 through 14. Again, my homework checks are done weekly, so nothing is due until next Sunday. The due date for Sunday is Sunday at midnight, so this is for, I think it's the 15th. You'll just load that stuff into OneNote, either take a picture and drop it in of your physical notebook if you did your homework on paper, or you can do it directly in OneNote. Either is fine with me. I do not care which one you want to do. Obviously, Mr. Kulik is not sitting at his computer at midnight to make sure that your stuff is in. It just needs to really be there before, he's looking on Monday. So if you're turning it in at, 12:57 or something on Sunday, that's not a big deal. I won't know the difference. I won't bother to check if it's there on Monday morning, if I'm looking at it then. You know what I mean? John Paul.
Do we also turn in our syllabus on?
You can turn your syllabus into OneNote also, or if you want to give me a physical copy, that's fine too. Really, either is fine with me. Either way is fine.